Yeah, we are talking about limits, right? Last time we did a bunch of sort of finding limits by plugging numbers into our calculator or just looking on the graph of a function. I wanted to do one more like that because I have kind of a cute example. This is an interesting example. I want to talk about this weird function. F of x equals sine of pi over x, like that. This is meant to be an example to demonstrate why sometimes this business about plug it into your calculator actually is not good enough to find the limit. As I said last time, we did a few examples. Well, let's just try this. Let's find the limit as x approaches 0 of this function. Sine of pi over x, all right? As x approaches 0. Using your calculator, the idea is you just choose some numbers really close to 0 and plug those numbers into the function and see what you get as the answer and see if you can make any kind of deductions based on that. So let's choose x values close to 0. How about, let's start with maybe x equals 0.1, and then I'll do 0.01, and I'll do 0.001 just for fun. All right? And you just plug these in using your calculator. Although you'll see actually in this particular example, you don't even need a calculator. For this, you get sine of pi divided by 0.1. But, 0.1 is 1/10. So dividing by 0.1 is the same as multiplying by 10, isn't it? I think so. This is the same as sine of 10 pi. Any trigonometry masters out there? Do you know what sine of 10 pi is? Yeah. It's not 10. Welcome back. 10? Yeah? 0. Yeah, it's 0. Why is it 0? Yeah, right. Remember the graph of sine looks like this, where this goes up to 2 pi, right? So the sine of 2 pi is 0, and then this repeats itself, right? The next time around it's 4 pi. The next time around will be 6 pi, and then 8 pi, and then 10 pi. So 10 pi is actually another one of these values where you get 0 for the sine. In fact, sine of any whole number times pi is going to be 0. Because also, this one's pi, this is 3 pi, right? Any whole number times pi, the sine of it will always equal 0. Anyway, sine of 10 pi is 0. Okay, what about this next close value? Sine of pi over 0.01. I can rewrite that in a similar way, right? The 0.01 is 1/100th. Dividing by 1/100th is the same as just multiplying by 100, right? This is sine of 100 pi. And that is also 0, right? For the same reason as before. How about this one? Sine of pi over 0.001, that's 1,000th. This is sine of 1,000 pi, which is also 0. We don't usually get all the way out to 1,000 pi, but it is 0, all right? Anyone want to make a deduction? What do you think the limit is? 0? Yeah, I mean, these are 0 every time. So I will say, it seems like the limit as x approaches 0 of sine pi over x is 0, right? But actually, this was an elaborate prank. In fact, the limit is not 0. I fooled you. Maybe I fooled you. I don't know. Maybe you could see where I was going with this. Actually, the limit is not 0. For example, let's just choose another number. How about x equals 0.009? All right. If I choose this one I really will need to use my calculator this time, because pi divided by 0.009 cannot be rewritten in any kind of convenient form. But I did this on my calculator. What I got is negative 0.34, which is actually not really close to 0 at all. I mean, I suppose it's kind of close to 0, but I would expect that if the limit really was 0, I would expect this number to be very close to 0. This is not really close to 0. All right. The moral of the story is sometimes just by some weird coincidence based on the values you picked, you're going to, you might get some kind of misleading information about what the limit seems to be. It is a fact that I actually cooked up these values specifically to give me 0 every time, even though I knew the limit actually is not 0. It's, well, what is it? So can I just say, the limit is not 0. I think the best way, if you really don't know what the limit is, it's best to just look on a graph of this function. So you can graph this on your calculator or on your computer or something, and I did this. I will show you what it looks like. It looks kind of crazy. What you have, let me just say, this function here, the y value is the sine of pi over x, right? So what I'm going to see on the graph, because it's the sine of something, the answer is always between 0 and 1. Because that's how the sine works. The sine of anything is always between 0 and 1. But when the x is near 0, this looks kind of like 1 over x. I mean, it's pi over x, but the pi doesn't really make a big difference. When the x is near 0, the thing you're plugging into the sine is kind of like going to infinity or minus infinity. So what you're going to see is something that looks kind of like sine, although it goes kind of crazy near the origin. Check it out. This is actually a cute little graph. This is what it looks like. So the values are always between 1 and minus 1 because the sign is always stuck between 1 and minus 1. But like I said, it goes crazy in the middle. All right, what you have is this kind of oscillation up and down, but the ups and downs, they go super fast as you approach the middle. That's because the thing you're plugging into sine is going like 1 over x, which goes to infinity when you get near the middle. Anyway, I think when you look at this picture, it's clear that actually the limit is not 0. When you go to the origin here, it's not like all the y values get close to 0, right? They don't. They just go crazy. Although some of the y values become 0, right? Like this one here, here. There are a bunch of y values that are 0. Actually, those are the same values that I picked for the points to plug in, right? So it is possible to get a bunch of values that look like 0, but there are many other values that are not close to 0. So the moral of the story here, just by looking at the graph, I can say the limit as x goes to 0 sine pi over x does not exist because there is no particular y value that this curve approaches, right? It kind of approaches all the y values from minus 1 to 1 at least. This is a very kind of wild graph. All right? The moral of the story is don't always believe what your calculator says when you plug in a bunch of numbers. Sometimes those numbers are misleading. All right? This is not really because of a calculator error. It's just because the numbers that I picked happened to fit a certain pattern that I didn't intend it. Actually, I did intend it. All right? Any questions about that? All right. Beware hidden patterns that you don't know about. Okay. I would like to talk today about a couple more, I would say, fairly simple concepts involving limits. They are one-sided limits and limits to infinity. So let's talk about the one-sided limits first. One-sided limits. If you know something about limits already, you probably already know about the one-sided limits. They are, the purpose of talking about one-sided limits is for examples that look something like this. If I have a function like this, maybe does that. A function which has like a jump in it, a discontinuity point, where it jumps from one value to another, but then continues after the other value. All right. Of course, the interesting point here is when x equals 2. Okay, so in this example, here in my picture there, the limit as x approaches 2, this here does not exist. That's because when I say what's the limit as x approaches 2, it means what do the y values get close to when the x is close to 2. And on this picture, I would say the y values don't actually have a specific thing that they get close to. Some of the y values get close down here, but there are some y values up here, all right? There is no single y value that is approached uniformly by the graph, because it sort of goes to two different places depending on which side of that 2. If you're looking like, if you're looking like on the left side of the 2, then it's down here, but on the right side, to the right, it's up here, right? And they're two different things, and so if I just ask you about the limit, we say the limit does not exist. That's because it kind of approaches two different values on the two different sides. All right? But you can, in this example, you can still say, like, okay, yeah, it does have two different values on the two sides. But if I only look at one side, then it does actually have a limit on the one side. And if I only look at the other side, it does have a different limit on that other side. And these are called the one-sided limits. And so the way that these are written is there's the limit from the left, and there's the limit from the right. And I hope you can tell on the picture which is which. The limit from the left is when you look only at this part, and the limit from the right, in this case, is when you look only at that part. All right, but anyway, the limit from the left, we write this way. This notation can be a little confusing. So it is as the x is getting close to 2, but from the left. And the way we indicate that is with a little minus sign like that. The limit as x goes to 2 from the left, that line there is a minus sign. It doesn't mean -2, though. It means +2, but approaching from the left. Okay, and put, f of x here. All right. What do you say? Can someone shout it out? What is the limit from the left in this example? I see people are showing me the finger, not the finger, but a finger. The answer is 1, right? If you follow the curve approaching 2, but from the left side, the curve goes to a y value of 1. So this is 1. Great. How about from the other side? It means you're approaching x equals 2, but from the right side, which means you should be following along the blue portion of the curve up there. I'll write this one in blue. This would be written lim x goes to 2 with a little plus, meaning the plus means from the right of f of x. And in this case, it is 2. That's because the y values along that blue portion of the curve, they approach the value of 2, the y value of 2, all right? Don't get confused with the filled in dot and the empty dot. Those are only relevant if I'm asking you about what is f of 2. In that case, you look right at this point and you choose the filled in dot rather than the empty dot. But if the question has to do with limits, you should be looking at where are the nearby points going to, which does not, you don't have to consider the filled in or the empty dot because you care only about the nearby values along the curve, either up here or down here. All right? So let me just say, this is called the limit from the left. This one is the limit from the right. All right? And they are easy enough to just read straight off of the graph if you know what you're looking for. Any questions about that? I thought, let's just say specifically what this means. So if I said in general something like lim x goes to a from the left of f of x equals L maybe. So if somebody writes something like that, what that means is, it means when the x, I'll say it in words and I'll write this. When the x is really close to a, but slightly less, like on the left side. When the x is really close to a, but less than a, then the y values are close to L. This is what that means. So I will say something like, as x gets really close to a, but x less than a. So it's on the left side, if you were looking at the graph, means x is less than a. Then the y value is close to L. This is what the limit from the left means. All right, and then the limit from the right is the same. that's written with the little plus. I will just say the same, everything's the same except it'll say instead x greater than a, right? When the x is really close to the a but slightly greater, then the y value approaches L. These are the one-sided limits. Limit from the left and the limit from the right. Any questions about that? It's pretty clear to just look at a picture and say what they are, as long as you know what you're looking for. All right. Oftentimes, those two, the limits on the two sides are often the same. So I will say sometimes these are equal. For example, here's a picture in which they are equal. How about if I had something like this, and then it just continues, but sort of from the same point, and maybe there's another point up there. All right. In this picture, lim as x goes to 2 from the left, let's just say what they both are. Lim as x goes to 2 from the right. And just for fun, let's also say what is f of 2. These three things all represent different ideas, although in certain examples they might equal each other. They might act just sort of coincidentally be the same, but they are different ideas. Can anybody want to shout out? First of all, what is f of 2? That is the y value exactly at x equal 2. Yeah, when x equals 2, you look at the y value here, you choose the filled in dot, and you get y equals 2. So f of 2 is 2 in this example. Because x value 2 has the y value of 2, it's the filled in dot. How about lim x goes to 2 from the left? Yeah, they're all saying 1, and they're showing me the one finger, the good one. Yeah, lim as x goes to 2 from the left, it is 1. That's because if you want to approach this point, there are, of course, two directions you could come into this point from. I'm going to approach from the left side. And the y value, as I approach from the left side, the y value becomes 1. All right? And the limit from the right, that means you come in this way. And from the right, you also approach the y value of 1. So these are both equal to 1. This is what I meant. I said sometimes they're equal, right? The limit on the left side is often equal to the limit on the right side. In fact, really, the only time they're different is if you have, one of those pictures like I had on the previous page. They're different. Looks like, this kind of thing, right? Two different points, maybe one's filled in. All right. In that case, the left side and the right side are different. But if the two curves actually meet up at the same point, even if that point itself is missing, the two-sided limits are the same. All right. And in this example, since the limits on the left or the limit on the right are the same, since they are equal, that means you can also say that the limit, what about that? The limit, like without the left side or the right side, this is just the overall limit. It also equals 1, right? If the left side limit equals the right side limit, then that means the overall limit exists, first of all, and it equals that same number. Actually, what I just said, I'm going to write that as a theorem. Theorem. This is a fancy, mathematical word just for like a true fact that you can prove. Now, in this class, we're not going to do a lot of proving of theorems. This one, I think, is fairly commonsensical. It just says, so what I'm going to say in more formal language, what I just said before. If the limit on the one side equals the limit on the other side, then the overall limit, like from no side in particular, exists and is equal to the same answer that you get from the two sides. So I'm going to say that in these fancy words. If the limit from the left of f of x is equal to the limit from the right of f of x, then the limit, like with no side, the two-sided limit, then this exists, first of all. And what does it equal? Well, it equals whatever those other two sides are. The two sides are the same, then the limit overall does exist. and it is the same as the two sides. And lim x goes to a f of x is equal to those ones over there from the left side, and it's also equal to the limit from the right side. Right? It's true. It's a true fact. If the two one-sided limits are equal, then the overall limit exists and is also equal to that same thing that the two sides are equal to. All right? Pretty commonsensical. We're going to talk about some theorems in this class that are not so commonsensical. This one, I don't think we need to talk about justification for it because it is pretty straightforward in my opinion. Any questions about that? So I said I wanted to talk about two more things about limits. The one was the one-sided limits. That's what we just talked about. The other is infinite limits. Let's turn the page here. Infinite limits. Infinite limits. All right. Some of you, I've just in talking about limits informally, I've seen some of you already are comfortable talking about infinite limits. This is something that we say sometimes about functions like this, for example, lim as x goes to 0 of maybe 1 over x squared. The graph of 1 over x squared looks kind of like 1 over x, but everything is positive because of the squaring. So it looks like this. You have this asymptote in the middle there, and all the y values go up forever. The limit as x approaches 0 of 1 over x squared. So first of all, I would say this limit does not exist because there is no specific y value that function approaches near x equals 0, right? The y values just go up forever. They don't actually approach any specific value. So it is true that this limit does not exist, all right? Because there is no y value that the function approaches. But we can be more specific. So more specifically, it's not just that there isn't a specific y value. We can say even more specifically that these function values, they go up forever. And the way that we write that is the limit as x goes to 0, 1 over x squared, equals infinity, all right? When I say equals infinity, I'm not trying to tell you that infinity is a number, because it's not. I don't know what you know about infinity. I know kids on the playground like to talk about infinity. I'm here to tell you in a safe environment. We can talk about infinity, but it's not a number. It is a thing. It doesn't count as a number. Mathematicians actually like to talk about infinity a lot. There is such a thing as infinity. In fact, I don't know if you're aware of this. It's true. There are different sizes of infinity. Did you know that? There's like, if you're a math major, you all will learn about this. There are some infinities that are smaller than others. Kind of mind-blowing. I like that kind of stuff. But anyway, for now, I'm not really trying to talk about infinity as a concept. So when you see this, what this means, when you see that, your roommate may look at your paper and say, how could you get infinity for the answer? Because infinity is not a number. Your roommate is correct. Infinity is not a number, all right? When I write that, what I mean is, this means when x is close to 0, the y values. Now there are a few ways that I can say this. Basically, I want to just say the y values, like, they go up forever. You say that in any kind of slightly more formal way you want. I'm going to say the y values become arbitrarily large. This is a slightly more professional sounding way of saying the y values become really, really, really big, all right? If I say things like really, really, really big, the natural question is, oh yeah, how big do you mean? I mean, as big as you want. That's what arbitrarily large means. Yeah?
Am I just supposed to ignore that beeping?
Oh yeah, sure. I will close it. What is the beeping?
I have no idea.
I don't know. door was propped, I think. All right, we'll see. Yeah, thanks. Still going. I don't know. Okay, yes. So when we say the limit equals infinity, this does not mean the limit exists. Like, it is still true that the limit does not exist. Okay? When I say the limit does not exist, I mean the limit doesn't equal any number. All right? But it is also correct to say the limit equals infinity. What that means is just that as you approach this point, the y values increase forever. They become arbitrarily large. All right? Similarly, you can talk about a function whose limit is negative infinity. That just means the y values go down forever. I can still hear the beeping. It's all right. So we can also say, I think everybody knows what this means, just so that we have it on paper. We could also say something like the limit as x approaches some point a, some function, is negative infinity. And what that means is the same stuff, right? As x approaches a, the y values become. I lift this phrase straight from the book. This sounds very weird to me. I'm sure everybody will know what I mean. Arbitrarily large negative. That's what the book says, which sounds like not grammatically correct or not the English language, but the y values become arbitrarily large negative. All right, that's what the book says. And on a picture, this would look something like this, right? This is on this picture. This looks like negative 1 over x squared. So it is a fact. The limit as x goes to 0. Negative 1 over x squared is minus infinity, all right? It just means as you approach that point, the y values, they go down forever. Arbitrarily large negative. Strange way of saying it, but gets the idea across. All right? Limits at infinity. Infinity is not a number. It's true. All right. Let's talk about. Okay. There are some examples that look kind of like this, but the limit equals infinity is not exactly the right way to express it. I'm referring to something like 1 over x, right? 1 over x looks like this. This side goes up forever. This side goes down forever. All right? What can we say about lim x goes to 0 of 1 over x? Unfortunately, this you can't say this is not equal infinity, and it also doesn't equal negative infinity, because when you approach, it's not like all the y values go up to positive infinity. It's like some of them do, and some of them go down to minus infinity. So I'm going to say this is not infinity or minus infinity. The best we can do in an example like this would be the one-sided limits, right? You can say the limit on the right side is plus infinity. Those are the values on the right side, which they go up forever. And the limit on the left side is minus infinity. Those values go down forever. So the limit overall is not infinity or minus infinity, but we can say lim x goes to 0 from the left of 1 over x is minus infinity, and the limit is still beeping. The limit from the right is positive infinity. All right? So you can talk about one-sided. I don't know if any of you were wondering. Can you get infinity on a one-sided limit? Yeah, here's an example. This is not all that special. All right. Any thoughts about that? Limits, infinite limits. That's what I'm talking about. I got something for you to try. How about, usually examples like this, I would draw like a graph of something and then ask you to tell me what a bunch of limits are. We did one like that last time. I would like to try the other way around. How about you invent a graph with these properties, I would like you to just draw something. It doesn't have to be like a function that you know the equation of. It's just, you just draw a weird picture that has these properties. Now that beep is annoying me. It wasn't annoying me before, but now it is. You did this. I have an idea about fixing it. Okay, see if you can draw a graph of something, just one function that has all of these various limits and values to it. All right? You know, your picture is going to look different from everybody else's picture, but it'll have certain similarities. See what you think. I'm going to do my card here and see if that stops it. How long should I wait before I'm not happening. Sorry. How's it going? Getting anywhere?
But it's like different. It's kind of like a piecewise.
Yeah, right. Yeah,
But they're approaching two different limits. I would have two piecewises.
yeah, so near x equals 0, it would break into two pieces, and then also near 3, it would break into another two pieces. Getting anywhere? Yep. Yeah, it has to go over here, because it has to approach x equals 0. But you want the y to be done still at an 2. So it doesn't have to hit that point, but it's going to end up Alright. 2 points. Yeah, you should start by just plotting those two specific points. The limits are the more interesting part.
I never got an idea of what's going to be
Yeah, you can't put it down there.
Yeah.
From the right, it's up here, right? Is that supposed to be on the point?
Yeah, this is the number, this is 5, and actually
Yeah.
like 3.
Yeah, so from the right, you're going to do, when you come in this way,
Yeah, this is.
it's,
It makes me from the right. So,
no, I love this.
that works. So it's coming from the. No, because I have this. Yeah, that's okay. I forgot about that.
But I don't like this part. This much of it is good.
Okay.
Because when I enter from the right, but when I come this way, I want to not let it go down correctly.
So this like.
Yeah, right.
Okay.
You kind of overshot it really quick.
Oh, yeah. So if this is a piecewise, isn't that 3 equations, right? That's okay.
Yeah, it's in 3 pieces.
Okay.
You guys doing all right? Got some overlapping curves there. Okay, so I like this part here. If I do approach this point from the right, it goes up to 5. It means that this goes like from the these two limits on the two sides are different.
Oh, yeah.
So they shouldn't, this shouldn't both be that, it should be. I like this picture, is then when I approach the right side. This should be like this one like it's bad, which means when I come in from the right side, what's going on? Yeah, that looks good. Yeah. Yeah, so as you approach zero, it should end up at one, that's right. Then when you come here, you can go over to two. It should go to five on this side. Like from the other side, it should go down. All right, let's talk about these. Sorry, I didn't get around to everybody. I don't want to spend too long on these. So first, you should just plot the points. I'm going to try and do it down here. F of 0 equals 1. So there's a point there. And f of 3 equals 2. So there's a point there. All right. I saw pretty much everybody started like this. And then the nonsense begins. Where are we going to go? I'm going to try to think of this about, let's think close to 0 first of all. There are two sides, of course. What happens on the left side? Is it still beeping? Don't know. All right. On the left side, it says the limit as x approaches 0 from the left is -2. So when the curve comes in here from over here, somehow the curve does not end up at this point. It ends up down here at -2. So you want to do something like this. I guess it's going to have to be an open circle because I already said that the point exists here. So you can't put another closed circle down here. It must be an open circle. And then the curve does something like that, right? Doesn't actually matter. I'm getting text on the big screen. I don't like that. That was my dear wife. Does that help if I do the moon? I don't know. We'll see. Okay, so from the left side, the thing, when it comes in from the left, it has to end up down at y equals -2, all right? I hope that makes sense. What about to the right of this point over here? It says when I'm on the right of 0, the y value actually ends up at 1. So this curve actually, it does arrive right there, right? From the right side, the limit of that thing is actually y equals 1. Now, I drew my curve sort of going up a little bit. That's irrelevant. You could have made it do whatever you want. That's just a little bit, all right? So I hope that your picture, at least near the origin here, looks something like that. Any questions about that part? All right, and how about over here, near the 3? Of course, you have this 1 point, but let's look at this part. The limit as x approaches 3 from the right is 5. That means when the curve is coming in from this direction, it goes up to y equals 5. So it does not hit this point. It goes up here somewhere. Sorry, I'm off my... It does like that, right? And it has to be another empty point there and another open circle there, just because I already have a filled-in point somewhere. So you have to make an open circle. All right? And then on the other side, so that's what happens to the right of 3. What about just to the left of 3? The y values go down forever, it says. So this part of the curve here, when I continue it to the right, it does not end up at this point. It doesn't end up anywhere. In fact, instead, it goes down forever. So it has to do something like this. Whoa, sorry. Something like this. Like that. There's some kind of a vertical asymptote there. All right? Something like that is what I wanted to see. Any questions about that? Any given persons will probably look different because your curves like in between could have gone other places, but this is what it should look like. It is a little tricky. If you actually wanted to write a formula for this, I suppose it would be a piecewise formula in like at least 3 pieces. Probably you need 4 pieces. You need like one special piece just for that point. And then one here, and one here. All right. Excellent. Great. What do we got? We got a few more minutes. That's enough for me to say a little bit about the next section. That was the end of limits on one side or the other, and then also limits going to infinity. All right. The next section in the book is what they call limit laws. These are strategies for finding the limit without using your calculator, just by looking at the formula. And this is actually the way that we're usually going to find the limit. I said last time there are some fairly simple tricks. For certain functions, we have to use much more complicated tricks, but we're not going to go there just yet today. I'm going to say usually limits on graphs are not very interesting. And I'll tell you what I mean by that. For example, here's a graph in which this one actually does have something interesting going on with the limit. Let's say this is at 4. So I would say near x equals 4, the limit is a bit weird. Like it's in this example, the limit is different on the left side versus the right side, okay? Near x equals 4. But on that picture, near all the other x values, the limit is not really weird at all. Like the function doesn't jump from one place to another. The values of the functions are not, there's not like an empty circle and a filled in circle somewhere else, right? Near all the other points, the limit just equals, near all other points, the limit of the function is just equal to whatever the value is at that point. Like, for instance, I didn't even write any y values in here. But in this case, you know, when you look at this picture, your eye is naturally drawn to this beautiful breakup point over here. But if you're looking at one of the other points on the graph, say near x equals 0, if I look at x equals 0 here, I would say f of 0, just estimating, looks like maybe 1/3, right? The y value at x equals 0. And also, lim x goes to 0 of f of x is also 1/3. I mean, that's just because where is the graph going along the curve? It's just going to the same place that the actual point is, all right? That's not exactly true here because the actual point is up here, whereas the graph is going to 2 different places. But on all the other points, there's nothing really interesting about the limit at all. The limit, as you approach some point, is just equal to wherever that point is, right? This is what I mean when I say usually the limits are not very interesting. Like maybe there's 1 or 2 points where something weird happens, but everywhere else there's nothing weird going on at all. So I'm going to say, this is kind of informal language, which we will say more formally next time. When there's no funny business, by which I mean like weird breaks in the graph or like a piecewise function that has a jump in it or something like that. When there's no funny business on the graph, I mean when you just have like an ordinary looking graph, which just is an ordinary looking curve, no weird stuff going on with empty points and filled in points or anything. When there's no funny business on the graph, we expect the limit as x approaches a of f of x. We expect this to be the same as f of a. That is, the limit, of course, this means where are all the points near a? Well, they're just going to be the same location as where the point actually at a is, all right? When there's no weird stuff going on in the graph, we will always expect the limits to behave in this way. And I can say, in particular, this is always true. of polynomials. Because a polynomial, the graph of a polynomial never has one of those jumps in it, right? It just does some stuff, all right? We talked about function value. Whoa. That on the first day. You know, the graph of a polynomial, it just looks like this, maybe. It goes up and down, maybe. But it has no jumps in it, no empty circle, filled in circle, none of that stuff, all right? In fact, this is also true of any rational function. I'm all zoomed out here. Also true for any rational function. Remember, that is a fraction with polynomials in the top and the bottom. Rational function. Graphs of rational functions, they look just like graphs of polynomials, although they might have vertical asymptotes somewhere. So it could look maybe like this. All right? Maybe it does that. But anyway, there's no jumpity jumps. There's no like points which are not there, but they're somewhere else, right? Those are the only things which can cause the limits to do something weird. Okay, so in all these cases, it's time to go. I'm just going to write one more thing. For any polynomial or rational function, we're going to have lim x goes to a of f of x is equal to f of a. And this is how we find the answer of the limit. This is how we find the limit, right? If I ask you, like, what is the limit of a certain function at a certain point? Well, if it's a polynomial or a rational function, all you got to do is plug this a inside the function. That's what you do. The fancy name for this is evaluating the limit by direct substitution. I would just say you just plug it in and you get the answer. All right? So this is what we'll do next time. Time to go. See you then. Don't forget that homework.